Hey guys, this is JB Mom from Planning C's Tutoring. In this video, we'll be discussing kinematics, or the equations of motion for introductory physics. Don't forget to use my referral code JBMon20 to receive 10% off on your next tutoring package. So these are the three major equations of motion that we'll generally be looking at whenever we're dealing with any kind of physics problem. There's a couple more that you can make out of manipulating these few equations. In fact, all these equations can be just derived out of like any one of those. But anyway, first we need to recognize what each of these variables refer to. So this variable Vx, that just refers to the velocity in the x direction. It doesn't necessarily have to be the x direction. It could be any particular direction. But if we use, like, let's say the y direction, remember we have a coordinate system, we have x and y. If we're referring to the velocity in the y direction, we would also need to be using the initial velocity in the y direction and the acceleration in the y direction. But for simplicity terms, I'm just referring to the x direction for now, and we'll be using the velocity in the x direction is equal to the initial velocity in the x direction plus the acceleration in the x direction times time. Time is not a member of space and therefore would not necessarily have to follow the dimensions of x, y, or z. The reason as to why we can just refer to it as x is because labeling x or y is very arbitrary. You don't necessarily have to label the horizontal as x and the vertical as y. That's just the standard, but we can always change it around. This could be y and this could be x, and you can use the y direction as x instead. Maybe if you use a three-dimensional plot, you can also label the generic z direction as x as well. Next, we have x right here by itself. Now this can get a little confusing. The subscript x just refers to the direction, whereas this x right here refers to the actual displacement, the final displacement. X naught or x0 refers to the initial displacement. Vxo refers to, or Vx naught refers to the initial velocity. Again, time plus 1/2 axt squared, 1/2 acceleration times time squared. Next, we have the the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the change in the displacement. This can also be referred to as delta x, which is, this delta just refers to the change in, or the difference between the initial value and the final value. Now, we can also be getting this 1/2 right here, this 1/2 term, by just manipulating the values of Vxo and Vx and getting like the idea that V average is equal to the initial velocity, or the initial velocity plus the final velocity divided by 2, and this is always equal to the change in the times, the change in the displacement, so the initial displacement, or the final displacement minus the initial displacement, which is just going to be x minus x naught in our case, x minus x naught, or we could also refer to as delta x, divided by the change in the y. This is just, or change in the time, is just going to be the t minus t naught, or divided by t, or delta t. If you manipulate this a little bit, you would be able to get the idea that this 1/2 comes from all that. Now, you might be able to notice that all of these equations do have something missing. For example, in the first equation, we have no references to any of the initial displacements or anything. So that would be a displacement independent equation. This has no references to x or x naught, so you don't necessarily need to know anything about displacement to figure out any of those information. Here, you don't have any information on the final velocity. Next, you don't have any information on the time. This is what we call the time-independent equation. All right. So now let's try out a practice problem using each of these methods. So let's use equation number 1 first. Let's remember Vx is equal to Vxo, the initial velocity, plus Ax times t. Let's say that you have a car. Starting at rest and moving in the positive x direction, or just moving to the right. And it's moving at a constant acceleration of positive 8.00 meters per second squared. You're trying to figure out how long would it be until it reaches a final velocity of 30 meters per second. Well, the things that we already know are the initial velocity, that's equal to 0 meters per second because it started off at rest. The final velocity, that's equal to 30 meters per second. And we're trying to, we also know the acceleration, Ax is equal to positive 8.00 meters per second, so that's 8 meters per second squared. And we don't know what the time is. Now, setting this up in just like a generic algebraic form, you would be able to get .30 meters per second is equal to 0 initial velocity plus 8 times time. When you try solving this, you would be able to get that 3.75 is equal to time, and just to keep up with units, you'd be able to get that this is 3.75 seconds. For the next problem, we can use the equation which is independent of the final velocity. So this is going to be x is equal to x naught plus Vxo t plus 1/2 Ax t squared. In this problem, let's say that you're just walking down the Golden Gate Bridge. You're just walking down the Golden Gate Bridge, and you accidentally drop an apple from the bridge to the water below. So again, you have the bay right there, and you dropped an apple from the bridge to the ground below. Well, the platform that you're standing on, the road, is about 67 meters from the water, from the sea itself. 67 meters above sea level in general. The question here is, how long did it take for the ball, or for the apple, to reach the water? So again, let's also just start off with our givens, what we have and what we're going to be able to do with it. Well, the information that we have is the initial height. Initial height is equal to 67 meters above the sea level. The final height, well, that's going to be at sea level, 0 meters. We also know initial velocity. Well, if any object is dropped, that means you didn't throw it anywhere, you just let go of it, which means it started off at 0 meters per second. And we also know the acceleration. Now, the acceleration, if you just drop something, and let's say that you're assuming air resistance, in this case, let's assume that we're neglecting air resistance. It would just be the force, or it would just be the gravity, or it would just be the acceleration due to gravity, due to the force of gravity. And that's going to be what we call g, which is equal to negative 9.8 meters per second squared. about on Earth. Well, if this is the case, we would pretty much just plug in all these numbers into the equation and you would be able to get final height, 0, is equal to 67 plus VXOT, initial velocity times time, which we don't know. Again, time is the question. Plus 1/2 times negative 9.8 times t squared. If you try solving this, you would be able to get, just plug it into a calculator or something, you'd be able to get that t is about 3.70 seconds. So it takes about 3.7 seconds to throw, or to just not even throw a ball, just drop a apple from the Golden Gate Bridge to the water below. Finally, we have, let's say, third problem. In this problem, let's say that, in this problem, we would be using the third equation, which is the time-independent equation. Remember, once again, it's just Vx squared equals Vxo squared. Vxo squared plus 2 times the acceleration times the change in x. I'm just going to write this as delta x. All right. So in this problem, let's say that you're trying to figure out whether or not the same apple that you dropped from the Golden Gate Bridge, whether or not it will ever reach 40 meters per second. Or in this case, a speed of 40 meters per second. In this case, velocity would be a negative 40 meters per second because it's going downwards. And we set our positive x in the upwards direction. But regardless, we're just trying to figure out whether or not the ball would ever reach a speed of 40 meters per second. Well, we still have pretty much all of the other information. Technically speaking, there are a variety of different ways that you can solve this problem. You already know how long it would take to reach the bottom, so you can try and figure out using that how fast it was going at the bottom and use one of the other equations. Or you can try plugging in 40 and figure out what the height is, the change in distance is. In our case, I'm just going to be using, I'm just going to leave Vx as a question mark. I'm still leaving Vx as a question mark, and I'm trying to figure out whether or not it's going to be greater than or less than 40 meters per second. If that value is greater than 40 meters per second, or the magnitude is greater than 40 meters per second, well, then it does reach 40 meters per second. Otherwise, it doesn't. So this is going to equal Vxo squared, which remains to be 0 squared, plus 2 times negative 9.8 times delta x. Well, remember we started off at, or our final distance, remember this is delta x, which is the final displacement minus the initial displacement, or x naught. Another way that you might see this is xf minus xi, the final minus the initial. Well, the final displacement is 0 meters above sea level, and the initial displacement is 67 meters above sea level. Plugging all of this in, we get a Vx value, or a final velocity value, that's equal to 36.24, or about 36.24 meters per second. This value is less than 40 meters per second, and therefore the ball never reaches, or the apple never reaches, gets to be 40 meters per second, never reaches the speed of not going to be 40 meters per second. Assuming that the water slows down the ball completely. Alright, that's going to be it for this video. Thank you all for watching. I hope you guys learned something new.